All right, folks, today what we want to do is we want to look at the standard free energies of formation, and we're going to look at getting these in a couple of different ways. One of these will be using delta G is equal to delta H minus T delta S, where we're going to use standard enthalpies and entropies to find the standard free energy. And so if you recall, to find the standard enthalpy of reaction, so delta H of reaction, what we can do is we could take the sum of the moles times delta H of formation of the products minus the sum of the moles times delta H of formation of the reactants. We can do the exact same thing for the entropy. We could find delta S for a given reaction by taking the sum, the moles, times delta S of the products minus the sum of the moles times delta S of reactants. And you can look up all of these values, heats of formation and then the standard entropies. You can look those up in any thermodynamic table. And finally, what we will do is we will look at calculating delta G from delta G of formations. So our first example, what we want to do is we want to look at this reaction. N2 plus 3H2 yields 2NH3, where you're given delta H of the reaction and delta S of the reaction. A couple of things that you want to remember as we're going through, anytime that you see that standard state signs, this degree sign on delta H or delta S or delta G, what we're doing is for solids, liquids, and gases, we're looking at them being in the pure form. They have a pressure of 1 atmosphere. If you're looking at a concentration of a solute, it will be at 1 molar. And the temperature, unlike the gas laws, standard temperature and pressure for thermodynamics, the temperature is equal to 298 K. So for what the information that's given here, we can take delta G is equal to delta H minus T delta S, and we can just plug in our values. So we can plug in negative 92.2 kilojoules minus our temperature, and the temperature is not given to us, but since we know it's at standard conditions, we know it's 298 K. And then the entropy we need to convert to kilojoules per Kelvin, so we have negative 0.1987 kilojoules per Kelvin. Where we plug this in, we'll find out that delta G is equal to negative 33.0 kilojoules. All right, so now we can actually find this in another way. The other way that you can find this is in one of those thermodynamic reference tables. They'll actually give you the standard free energy of formation, so delta G sub F. And this is just looking at the free energy change for the formation of 1 mole of the substance, just like whenever you're looking at the enthalpy of formation. But now we're looking at delta G of formation. So delta G of the reaction is equal to delta G of the products minus delta G of the reactants. And this would be better expressed as writing the sum of the moles times delta G of formation of the products minus the sum of the moles times delta G formation, should be delta G of formation of the reactants. All right, so let's revisit this same reaction. We have N2 plus 3H2 yields 2NH3. We're asked to find delta G of reaction, and we're given the free energy of formation of hydrogen, of nitrogen, and of ammonia. So notice that just like for enthalpies of formation, if you have something that exists in its standard state, that its delta G of formation will be equal to 0, which is why hydrogen, H2, is equal to 0, and nitrogen, N2, is equal to 0. So to find delta G of reaction, what we can do is we can take our products. So we have 2 moles of our products times its delta G of formation, which is negative 16.5 kilojoules per mole, minus the reactant's contribution. Normally I wouldn't write this out since they're both 0, but I want to go ahead and show you how we would do that. So we would have 1 mole, this is from the N2, times its delta G of formation, which in this case is 0. So we probably don't need a calculator for this part, plus 3 moles times that 0 kilojoules per mole. Close our brackets off. So this whole term goes to 0. So delta G of reaction is equal to negative 33.0 kilojoules per mole, or sometimes we'll just write it as kilojoules. But this is our answer for this reaction, which is exactly what we got for using the previous method where we use delta G is equal to delta H minus T delta S. There's a couple of different ways you can find the free energy for a reaction under standard conditions.